All right. Well, next we have Dr. Stephan Boyer, a Google Chem Informatics scientific advisor. He is a researcher in the interdisciplinary space of chemistry and computer science. He pioneered the use of computers to curate patents and scientific literature in the life and physical sciences. Other than working at Google currently, his work in the synthesis at Did someone say something? At Norvis and in data science at IBM Research. Today, he will help us better wrap our heads around chem informatics and the impact it has on drug discovery and the prediction of new therapies and materials.
Okay, hello. Let me get this started here. And can everyone see my screen now? And you can hear me. I'm unmuted?
Yes, we can hear you. We can see your screen.
Okay, so thank you very much for the opportunity to talk about what I do. So my talk's going to be broken down into two parts. The first part, I'm going to try to review chemical informatics, some of the fundamentals, primarily because without understanding a little bit of background, then you may not understand what I do in a day-to-day. But we'll get there together. So I was told that I'd be addressing a range of students from middle school to high school. And there are a lot of chemical issues and a lot of ground to cover. I thought I'd start with just a simple understanding of the atom, because, you know, molecules are made up of atoms. And when I went to school, the atom, we were considered to be basically consisting of protons, neutrons, and electrons. And that was sort of it. And then once when I was at Albuquerque, I went to the Atomic Museum, which I would encourage everybody to go to if you get a chance to, the Nuclear Museum. And they had this poster here. And I was thinking about how our understanding of chemistry has evolved. So from this sort of basic understanding of the atom, we've now evolved into subatomic particles and understanding subatomic particles as well as the bigger molecules, which we'll get into. But what I was most impressed with is the size of things. And if this is a helium atom and this is the nucleus of the atom, this size, and if this nucleus right here were, let's say, 3.9 inches, 4 inches, or 10 centimeters, then how far away would that electron be that's sitting out here? And it turns out that if this were the size of the nucleus of the atom, that electron would be 6 miles away. And I thought, wow, you have to think of things in terms of different proportions and how that's a big distance between the nucleus and the electron, 6 miles. And that's pretty amazing. And the reason I want to point this out is that as we go down this path of understanding chemistry, this is sort of the Newtonian view of chemistry. And Newtonian physics, we could maybe put a man on the moon with Newtonian physics, but we could not have built a nuclear reactor or an atomic bomb with Newtonian physics. We had to go to quantum mechanics. And so I would encourage the students that as we go forward, realizing that we're evolving in our understanding from this world of, shall we say, Newtonian physics to quantum. And this progression is very obvious in chemistry as well. So let's move on and go to a bigger molecule from helium. And let's look at just a simple molecule like ethanol. So I tried to pick a molecule everybody might appreciate. Ethanol is in beer, and if you drink alcohol, it's in a martini or whatever, a gin and tonic. It's the active ingredient of cocktails, you might say. And it has 2 carbon atoms, and you can see here it has methyl. We call this with 3 hydrogen atoms. So the white are hydrogen atoms, the dark gray are carbon atoms, and this is an oxygen atom. And, you know, ethanol is a pretty cool molecule. You can drink it, you can enjoy it. But it's very closely related to methanol, which is the same molecule, but without the CH2 in here. It's one carbon less. And, you know, if you drink methanol, you'll go blind. And if you drink ethanol, you'll maybe get high or enjoy yourself, or, you know, it has other effects. So there's very dramatic functional differences between a molecule like ethanol and methanol. And this is pervasive throughout all of chemistry. And so one of the things to understand about chemical informatics is how we go from a chemical name, say like ethanol, to this stick diagram, or to this ball and stick diagram, we call this. And so in order to do that, you have to take this word ethanol or the word methanol and make it into a machine readable format in order for it to project it as an actual molecule, what it looks like. So we have to go from the text to the structure. We call that a name to structure algorithm. And in order to do that, you need to have a fundamental understanding of different formats for machine readable forms of molecules. So in the beginning, we had something called mole files. So if you took a molecule like benzene and you wanted to make it a machine readable form of a molecule so that you could actually look at it on a computer screen or work with it, you had to convert this word benzene into this mole file, which is a three-dimensional description of that molecule. And what this does is it basically says, you know, atom number 2 is connected to atom number 3 and atom number 1, and it builds what we call a matrix diagram of the molecule. And then I'd say sometime later in maybe the 70s or 80s, Dave Weininger came along and came up with a simpler way of defining machine readable forms of molecules, and he called them smile strings. And this is an example of a smile string. And Dave made a huge contribution to the world of chemical informatics, because now we could take the word benzene and we could define it as the smile string, put that into a computer, and then actually visualize the molecule in 3D and rotate it and do all these things. So Dave was quite a character. And anyway, he lived out in Santa Fe, New Mexico, and bought his own big jet, flew it around, had a great time. Anyway, then more recently, we came up with something called, we needed unique identifiers. And so, because you can have conflicts between smile strings, and a group of people got together and they came up with something called INCHIs. INCHI stands for International Chemical Identifier. And it's sort of like a domain name. Basically, it defines a molecule as, here's the molecular formula layer, here's the carbon layer, and here's the hydrogen layer. And we had this bright idea of defining molecules as domain names. But then as the molecules got more complicated, again, this is a simple molecule, naphthalene. And here you can see C10H8 is the molecular formula layer, here's the carbon layer, and here's the hydrogen layer. And as we progress to more complicated molecules, introducing things like stereochemistry and carboxylic acid groups and radioactive atoms and things like that, we had to define more layers. And so you have a charged layer, a stereochemistry layer, an isotopic layer, and a fixed hydrogen layer. And these domain names, or these INCHIs, just like domain names, can get quite long and complicated. So what people started doing is they took these INCHIs, which are like domain names, and they put them into a hash program similar to something called MD5. MD5 is an open source hash algorithm from MIT, and if you don't know it, just Google it. It's a very cool algorithm that enables you to take any character string, put it in, and it generates a 32-bit what we call an INCHI key, which is a unique identifier. And so that's basically the background. And what I just reviewed with you is several, shall we say, years of chemical informatics. But what you should know is that there's several machine readable formats of molecules. There's a mole file, a smile string, an INCHI, and an INCHI key. And I'll be using those terms. And then you have this ability of going from a chemical name to a smile or another machine readable format. We typically use smile strings, and then you have to have a way of drawing the molecules, and we call those molecular editors. And there's some programs like ChemDraw. There's an open source one called ChemSketch from ChemExons. It's called ChemExon Marvin. So if you want, you can download those and use those to actually draw the molecules. So now we'll get into the second part of this talk, and that is why chemistry. And chemistry is really, it's been said from a professor from Caltech, it's a gateway science. All biology depends on it. Physics sort of depends on it. Material science, and it's a great way for maybe like a lot of things. I mean, molecules, for example, can make money. So one of the objectives of getting a good education is getting a job and making money. And I just put on here some examples of molecules. And these are the revenues that were made from this molecule in 2019. So in the top, we have some anesthetic molecules. And as you can see, this simple molecule here made $4 billion last year. This one made 1.6 billion. So, and then these are some molecules. These are an anti-diabetes drug, respiratory disorder, immunology. So molecules can be very useful for making money. They're also, in addition to that, they're useful for curing diseases. They're useful for materials, for plastics, energies, batteries, and they impact our lives in every way you can imagine. So a good understanding of chemistry and understanding molecules and what they do is, in my opinion, essential. I put a URL here to work done by a professor at University of Arizona, where if you click on that link, you can get a poster, and that poster will show you every single drug, it'll show you the top 100 or 200 drugs, and it'll show you how much money each of those drugs made, if you want an example of more examples like what I'm showing here. So now, oh, thank you. Whoops, there went my slides. Okay, there we go. Now, before we go on to what I do, actually, thing to understand about molecules is they have a lot of attributes. Just like a person has an attribute, they can be tall or short, they can have blonde hair, brown hair, blue eyes, brown eyes, green eyes. You have all these attributes associated with a person. They could be a football player or a scientist or movie star. And so can molecules have attributes. So they have what we call physical attributes. If it's a solid, it could have a melting point. It could have a boiling point. Water boils and it melts and it turns into ice cube. If you freeze it, it turns into an ice cube. It has a melting point. It has a molecular weight, a molecular formula, and so forth. And these attributes can more or less be, these physical attributes can more or less be calculated at this point. They have spectral attributes. Every molecule has a different IR, infrared spectra, a nuclear magnetic resonance spectra, NMR, mass spec, which has its molecular weight, so forth. And molecules have legal attributes. A molecule is patented, and it could be patented as a drug, like the ones that I showed you previously. And that molecule is owned by a company, and they own the rights to make money off of that molecule. And so there's the legal status to the molecules. Who owns it, whether it's owned by a single company or multiple companies, foreign filings, expiration dates of these patents. These are all what we call legal attributes. And then there's also, say, functional attributes. A molecule could be patented as a pesticide or a plastic or an explosive or a refrigerant or a drug. So there's all these functional attributes. So one of the things that chemical informatics tries to do is it figures out what molecules are useful and for what purpose and what are the various attributes associated with that molecule. And just as an example, this is ethanol going back, and this just shows you a spectra. Here's an example of what a spectra, this is a nuclear magnetic resonance spectra for this molecule. So this is just a quick example of what a spectral attribute might look like. So if you take this molecule and you put it in a solution and you put it between two magnets, the electron spin change on these hydrogen atoms gives rise to this spectra, and that is very defining the molecular structure of this molecule. Okay, so now what do I do? So with that background and understanding of the tools of chemical informatics, one of the things I'm very involved with is what we call finding dark data and using that for scientific discovery. How do you know what molecules have been patented for drugs or for plastics or materials? And so we do a lot of searching. And so the problem is, one of the problems, it's not the only problem, but one of the problems is how do you keep up with all the publications, the books, and all the materials that are available today? There's so much, you can't read it all. And so I say it's all content and no discovery. So the question is, can we use computers to actually read documents, identify critical entities, and perform meaningful associations that help us with our work? And so I say there's gold in them there documents. The only problem is we can't read them all. We can't read all the books we want to read. We can't read all the journal articles and so forth. So can we use computers to do this? So here's a picture of a patent. You're probably familiar with what patents are. That's a way you can preserve the properties of, say, a molecule. And patents have data in them both as text and as images. And so one of the things we do at Google Patents is we use computers to read these documents and extract all the data from the text and extract the data from the images as well. So here's an example. This is a text from a Novartis patent. And if I were to ask you, what is this molecule? This is a rather long, complex chemical name for a molecule. But even people knowledgeable of chemical nomenclature would have a hard time knowing that that molecule is that structure. And so what we do is we use computer programs to actually read this text, understand that this is a chemical word, and put it into a program that will convert that word into this structure. And it has to know that this A is not part of the name, for example. And that's rather complicated technology. I won't go into how that's done, but there's a whole 2-hour talk on how that's done. But the end result is we can take a paragraph like this one here, and we can convert that paragraph into a machine readable form of a representation of what that paragraph says. So here is the paragraph to a solution of this was added this and that, and it's basically a recipe. And what this paragraph, once you put it into these programs, it converts it into these machine readable forms. So we have all these molecules as smile strings or as Inchi keys, and we can then put that data into a database. And we can very quickly use computers to look up their spectra data, their melting points, and so on and so forth. And then you run into other problems, like, well, what about a molecule like this? This is a drug called Valium. And Valium has a trade name. It has a generic name, diazepam. It has a ID number, for chemical abstract registry number. And depending on what country you're in, it has 149 names. And so you have a problem with, well, how do you convert all these names? And so that's the idea of using chemical informatics. We can convert all these names into a single structure. And so this is just to give you an idea of some of the different iupac names for that same molecule. And they're not all correct. They're variations of the iupac. iupac is the International Union of Pure and Applied Chemistry. But these are the different types of chemical names that people can use to define that molecule. And the poor scientist, he just wants information on Valium, but it's published in all these different sources. in different formats. In Medline, medical journals, they use the word Cetapam or diazepam. In a patent, they'll use one of those complicated iupac names. And chemical abstracts, they use it as refer to it as an ID number. And so by having the content, the molecule as a machine readable format, you can actually search across all these different collections that come up with it. So at a high level, how do we do this? We basically start with a document, and we start with identifying the chemical entities. And once we identify those chemical entities, we extract the chemical names selectively. And then we take those names and we put it into what we call a name to structure program. And it takes that chemical name and it converts it into one of these machine readable formats that I described earlier. So it converts it into a connection table, converts it into a smile string or an INCHI key. And then once you have that as a machine readable form, you can do all kinds of things. And then the next big problem is, how do you scale this? So, we take the word valium, we put it into a computer, and we convert it into a machine readable form. We take the word benzene, we put it into a program, and it goes into this machine readable format. And we do this on millions of documents. In 2009, when I was working at IBM Research, we benchmarked the ability to do 1 billion pages in 3 hours. At Google, of course, we have more computers and we can do this very, very effectively. And so what we did more recently is we took all the patents from 138 countries. We took all the Google Scholar and all Google books. And the first thing they did is they put it through a program that Google developed to translate the data into English. So we took all the Chinese patents, translated them to English, the Russian patents, the Korean, you name it. You pick a language and they translated it into a common English language. We then did natural language processing, which is what I showed you, identifying selected entities. And by the way, we don't just do this for chemical names. We extract all the diseases, the proteins, the genes, et cetera. And so we do this name to structure processing. And then we map it. We map the entities as we identify it to various ontologies. In this case, it's a ontology concept identifier, gets a unique identifier, gets assigned to everything that gets extracted. And then we put it into this great big database in the sky called Google BigQuery. And the database is being made publicly available later this week through NIH. We're actually donating almost 50 billion entities extracted. And thank God they have all the computing resources to do this work. The folks at Google have been kind enough to support this and fund this effort. And so we basically try to identify every molecule on every page of every document, every protein, every disease, and show for medical subject heading codes. We because of copyright issues and so forth, we only donate the molecules derived from patents, but it's a very important capability. And now you can actually go and do structure, substructure searching for any document that contains that. And we put it into this BigQuery environment. And I think some of the earlier speakers mentioned Kaggle. You can use Kaggle or Python or SQL, structured query language, to query this. And in this big environment in the cloud, we not only have all the data that Google's donated, but we have all of PubChem in there. We have Kemble, Targ, a lot of different databases. And the idea here is that you can then apply artificial intelligence. You can do clustering, visualization, post-processing, machine learning of the data. So the challenge going forward is we have this environment, which I've quickly tried to describe to you. We have input as, say, smiles or a molecular structure. So you want to put a molecular structure into this resource, and you want to be able to semantically map it to all of the other content that associates that attributes of that resource, and you want to output the attributes. So put in a molecule and tell me that it's an adhesive or a cure for a bacteria or whatever. Or alternatively, you have a list of attributes that you want, and you say, I need a better adhesive, or I need a better drug for this disease, and you want to put in your attributes, and you want to output a list of molecules that would have those properties. So this is the dream. It's not realized totally, but we're on a path to come to this dream. And with that, I think I'll conclude. And if you take away only one thing from this talk, take away this list of resources. So if you're at all interested in chemistry or computer informatics, there are these 5 resources. One is Data Warrior, which is probably, it's all free. You can go to this website and download it. It's by Thomas Sanders, and it's probably the most powerful tool. You can do visualization of molecules, compute its polar surface area. You can look things up. It's phenomenal. Just take my word for it. It's wonderful. PubChem is a web resource from NIH, National Institutes of Health. You can go to PubChem and you can put in whatever your question is a word or as a smile string, and you can find just about anything there is to find out about that molecule. Orange is a really cool program for doing data mining. It's from a European university. It's all free. You can download it as a desktop tool, and you can spend the next month just looking at videos on how to use it, and it's fascinating. Google Patents, of course, is a resource. You can go there now, and you can do structure, substructure searching and find any molecule that occurred on any page of any patent. And you can download those molecules, and it's a wonderful resource. And then there's Kaggle, which is I put that in there because it's probably the most used database in the pharmaceutical industry, in that it's manually curated and it's very high quality content. I should probably have put in there the EPA database. That's another very good resource. But if you go to EPA CompTox database, that's another resource. So I think I'm over.
No, you're fine.
Okay, I'll stop this presentation. I'm sorry I went so fast, but if there are any questions, please feel free to ask.
Let me just check the YouTube live stream again in case anyone's on there.
So a lot of ground to cover.
Oh, Dr. Boyer, there's a question in the chat from Evan.
Okay. How do I get to that? I just click this. All right.
Oh, I can just, oh yeah.
Sure.
Is MD5 used for one-way encryption for passwords?
You could use it, but I don't recommend that. MD5 basically takes any character string and you put it into that program, and it creates a 32-bit hash. So you could take your name, or you could take your password and encrypt it. There are systems where you can put in the hash codes, and they're lookup systems which will do reverse lookup. So that's one of the risks you run. But it's fun. I mean, you could take, like, I don't know, a novel and put the entire novel in and encrypt that entire novel as a 32-bit hash. People are doing this now with DNA strings and protein strings or amino acids and things like that.
Oh, Arun also asked, how can someone circumvent salting?
How can you circumvent salting?
Salting.
SALTING.
Well, in terms of if you recognize a drug, like say benazepril, and it's used as a benazepril hydrochloride. So that's a post-processing issue, and we have tools that will go in and take the molecular content that we've curated through computer curation, and we post-process it, or you can post-process it, and say we want to strip off all the salts. And so there are tools available publicly that you can do things like that. One of them is a program called KNIME, Knime, and you can download these KNIME protocols and run them over your content, and it'll desalt all the molecules and like that. With this idea of computer curation, you run into problems of chemical names versus fragments, and it gets rather complicated. I couldn't cover everything, but there is a whole post-processing of the data that has to happen. And I should emphasize that it's not perfect. We got a lot of misspellings. We got a lot of names that we identify as one chemical and it comes out as another for various reasons. So it's a messy area, but that's the bad news. The good news is it's pretty darn hard to read 1 billion pages of patents in a few hours. And without this kind of computer science, computer technology, we would not have been able to do that. You'd have to go to a library and start flipping pages.
So sorry to cut everyone off, but we're a little low on time. So Dr. Boyer, thank you so much for your awesome talk.